our third 2020 Nobel Laureate in Physics, Professor Andrea Ghez. The title of her talk is From the Possibility to the Certainty of a Supermassive Black Hole. Andrea Ghez earned her PhD in physics in 1992 from the California Institute of Technology. The following years, she held a Hubble postdoctoral research fellowship at the University of Arizona. Professor Ghez has been at the University of California in Los Angeles since 1994 and became full professor in the year 2000. In 2014, she became the head of the Galactic Center Orbits Initiative at UCLA. Andrea Ghez has been pushing the frontiers of imaging at near-infrared wavelengths using the Keck telescopes in Hawaii. Her masterful use of laser-guided adaptive optics allowed her to make detailed mapping of the orbital motions of resolved stars close to the galactic center. The ultimate goal was to uncover the nature of the supermassive object lurking in the innermost part of the Milky Way. Professor Ghez, we are excited to hear about your fascinating discovery.
I'm so grateful to have the opportunity to speak in this forum. Before I begin, I'd like to dedicate this talk to two people who were very important in my development as a scientist, but are no longer with us. First, my father, Gilbert Ghez, who taught me to be curious about the world of numbers and to find their delight. And second, my PhD advisor, Gary Neugebauer, who taught me the importance of paying attention to data above all else. The work that is being recognized is a 25-year-long project that I began when I first started my faculty position at UCLA. UCLA was my dream job because it gave me access to the newly constructed Keck telescopes, which are the largest telescopes in the world. And I was interested in developing new ways of using this telescope to study black holes. I like to begin my lectures with the question, how do you observe something you can't see? This is an essential question if you want to find and study black holes, because black holes are objects whose pull of gravity is so intense that nothing can escape them, not even light. The story that I would like to tell you today is how we've been able to find a supermassive black hole at the center of our own galaxy, and this has provided us with the best evidence yet that these exotic objects really do exist, but it's also provided us with a wonderful laboratory for studying the fundamental physics of black holes, and in particular, how black holes warp space-time, and what role black holes play in the formation and evolution of galaxies. While the black holes are relatively exotic objects and require pretty exotic physics to properly describe them, the way I want you to think of a black hole today is an object whose mass is confined to zero volume. So despite the fact that I'm going to talk about objects that are supermassive, and I'll get back to what that means, they have no finite size. So what does this mean? This means that if we think about density, which is mass divided by volume, density goes to infinity. And in physics, anytime you have a number going to infinity, this is known as a singularity, which is equivalent to a giant red arrow that says you don't have your description of the physical world quite right here. So in fact, this is what makes black holes so interesting, because it points the way forward to understanding a deeper way of thinking about physics. Today, we don't know how to make the world of general relativity, which describes gravity near highly gravitating objects. So that's what Einstein is so famous for, work together with the study of quantum mechanics, which is the study of things that are very small. And black holes are both. They have tremendous gravity, and they're infinitesimally small. So when we understand what a black hole is, we'll be able to presumably make these two fields work together. But in the meantime, fortunately, there is an abstract size that we can think about that's quite important to the studies of black holes. And this is known as the Schwarzschild radius. And this is the size that if you can compress an object down to its Schwarzschild radius, and in fact, every object has a Schwarzschild radius, gravity will overcome all other known forces, forcing the object to become the infinitesimally small object of a black hole. So if we think about the Earth, and we could figure out how to squeeze it down to the size of a sugar cube, it would become a black hole. Now, fortunately, the Schwarzschild radius is actually quite simple to figure out. It just scales with mass. So if we were to look at a more massive object like the sun and scale it down to UCLA's campus, I couldn't help but put UCLA in there, it would become a black hole. So this notion is important because it not only defines what a black hole is, but it gives us a way of demonstrating or proving that a black hole exists. We need to show that there's some mass confined to at least within its Schwarzschild radius to claim a black hole. So in astrophysics, there are two kinds of black holes that we talk about. And in fact, they're a wonderful example of the interplay, the different ways that science proceeds. So in the first kind that I'm going to call the ordinary mass black holes, as if there could be such a thing as an ordinary black hole, are black holes that were thought from theoretical work that thought about what would happen at the end of a very massive star's life. So a star that starts off with more than 30 times the mass of the sun, it's thought at the end of its life, it's going to become a supernova. And what we're seeing here is that the outer layers explode off into interstellar space, and all sorts of exciting and really important things happen here. But for the point of view of this talk, what's interesting is what happens at the middle. In the middle, gravity overcomes all other known forces and is expected to become a black hole that has roughly 10 times the mass of the sun. So this was identified from theory and then subsequently verified by observations. So we have wonderful evidence today of the existence of these stellar mass black holes. Now, the story of the supermassive black holes is quite different. And by supermassive, I mean 1 million to 1 billion times the mass of the sun. This is a story which is led observationally. And observations of galaxies, and in this picture, almost every object in the galaxy is a galaxy. Only one object in here is actually a star within our own galaxy. So let's focus on the top left corner here. This is a galaxy. So this is a very different scale than the last picture that we were looking at. We were looking at a single star. Here, we're looking at a galaxy that has 100 billion stars. So it's a really different scale. And there's actually nothing in this picture that suggests the existence of a supermassive black hole. Because what this picture is that taken at optical wavelengths, which is what your eye detects. So you're sensitive mostly to starlight. So the idea of supermassive black holes residing at the heart of these galaxies came from radio pictures. Radio pictures of a tiny class of galaxies known as active galactic nuclei. And the name says it all. We think the nuclei, or the center, is very active of the galaxy. And so this is a very different picture. So at radio wavelengths, so somewhat akin to where your cell phone works. And you no longer see the starlight, but rather you see these jets of emission emanating out from the center. The whole galaxy is roughly in a modest scale at the center. So these very energetic jets, combined with the fact that the emission from the center of the star, or sorry, center of the galaxy, looks unlike anything emitted by stars or gas, led people to suggest that perhaps it's a supermassive black hole that's driving all this energetic phenomena. And in particular, it's a black hole that is dining or feasting or accreting a lot of material from its surrounding. So these, you could say, are like galaxies that are having a Thanksgiving feast. Now, this led people to think about the possibility that perhaps all galaxies harbor supermassive black holes at their centers, but these are rather stealth black holes, or rather black holes on a diet, because they don't have the material around them to light them up. Because remember, black holes themselves don't emit any emission. And in fact, this galaxy, which is the one we were zooming in the galaxy picture, looks very much like what our galaxy would look like if we could get outside it and look back. In fact, our solar system is roughly halfway out. So galaxies in general are flattened disk-like structures. So if we're going to ask this question of, do all galaxies harbor supermassive black holes? Or really, more profoundly, do these supermassive black holes exist? Our galaxy is simply the best place to look. because it's the closest example of the center of a galaxy we'll ever have to study. It's 100 times closer than the next closest galaxy. Now, so the pro in studying our own galaxy is that it's close, the center of our own galaxy. The con, because in life, usually every time you get a pro, you get a con, is that we're in this flattened disk-like structure. We're about halfway out, and we're looking through the galaxy to the center. So this is a picture of our own galaxy. If you could get out to a dark site, this is actually taken from the side of Mauna Kea. And what you see is the galaxy, the plane of the galaxy. It's lit up with stars, so you see it as a band of white light, or that's why it gets its name, the Milky Way. But in the middle of it, you see a dark lane, and that dark lane is dust. And dust is like smog in LA. It's very good at absorbing optical light. So we can't see through the center of the galaxy, through the galaxy at optical light. So if we think about the ability of light to penetrate from the center of the galaxy to us, optical light, what our eye detects, only 1 out of every 10 billion photons or light packets makes it from the center of the galaxy to us. In contrast, if we go just slightly longward of what your eye detects to the infrared, which is where your TV remote control works, 1 out of every 10 photons makes it to us. So in fact, you can see or perceive what's happening at the center of the galaxy if you go to infrared wavelengths. So a key to this work has actually been the rapid development of infrared technology over the last 30 years. So if we want to prove most directly the existence of a supermassive black hole at the center of our galaxy, the most direct way that we can do this is by watching how stars move. So stars move under the influence of gravity of whatever's inside their orbit. So their orbit, by measuring how fast it goes around and the size of the orbit, you can figure out how much mass is inside the orbit. This is just due to gravity. It's for the same reason that planets orbit the sun. So these stars are orbiting the black hole or whatever is inside its orbit for the very same reason. So if you want to show that there's a lot of mass confined to a very small volume, it's the stars that are as close to the heart of the galaxy that are the keys. So in a sense, we're inward bound in order to carry out this experiment. And this actually tells you very much why I was so interested in getting access to the Keck telescopes. So as I said before, the Keck telescopes are the largest telescopes in the world. And we characterize telescopes by the width, or the diameter, rather, of the mirror, the collecting element. And these telescopes, there are 2 of them, each one has a mirror of 10 meters. So to give you a sense of scale, this is equivalent to the width of a tennis court. Now, the campaign promise of large telescopes are twofold. One is that with a large telescope, you should be able to see things that are very faint. You can think of it as a light bucket. The larger your telescope aperture is, the more light that you can collect in a given amount of time. So for a typical astronomer, you're interested in seeing things that are faint, which is equivalent to things far away. And this is effectively a history lesson in many cases, because it takes light a finite amount of time to travel to us. Now, what I'm interested in is actually the second campaign promise, which is the idea that large telescopes, the larger the telescope, the finer the detail that you can see. So this is called angular resolution. And the analogy I like to make here is it's like the painting technique of pointillism. And the closer you get to the painting, the better your ability to resolve those individual dots. So that as you go closer to the painting, you're improving the angular scale of those dots. Now in astronomy, the equivalent is by getting a bigger telescope, you should be able to see smaller structures out in space. Now, the challenge, or why this second campaign promise has been so difficult to achieve, is the Earth's atmosphere. The Earth's atmosphere is great for us. It allows us to survive here on Earth, but it is a total headache for astrophysicists because it distorts our images of astronomical objects. So this is an animation of data that we took early on of the center of the galaxy, and there are 5 bright stars that are seen or in this picture. And if there were no atmosphere, the structure of each star would be equivalent to the smallest structure that you're seeing here. and rock solid, as opposed to something that looks more akin to a bug splat pattern. And it's actually rather profound if you think about this, because the light that we're collecting here came from the center of the galaxy. It actually took this light 26,000 years to travel from the center of the galaxy to us, and it's in the last 30 microseconds that it hits the top of our atmosphere and becomes completely distorted. So I'm interested in ways of overcoming this, this problem, because otherwise you can't get to the promised resolution of a telescope. And over the last 25 years, there's been a tremendous revolution in the ways that we've done this. So this is an experiment that, as you'll see in a moment, is benefited by time, just the duration of how long you've been making the measurements, but it's also benefited tremendously from the advancements in technology, which has improved our ability to make these measurements. In the beginning, we used something fairly straightforward and simple, which required lots of computational power, but very little hardware. And then in the last 10 years, we've gone on to a much more sophisticated hardware-based solution. And in fact, this is nicely connected to the military, because it turns out the military cares about seeing both up and down through the atmosphere. So they were developing techniques as well. So in the early 90s, there was a huge leap forward in our ability to correct for the distorting effects of the Earth's atmosphere. This new technique of adaptive optics, the way I like to describe adaptive optics, or even the problem of the atmosphere, you can think of the problem of the atmosphere in two ways. One is as a river that's turbulent and moving by you quickly. And the equivalent of seeing our astronomical objects is like seeing a pebble at the bottom of the river. And that moving river makes that object look distorted because of the turbulence in the river. So our job is to take that turbulence out of our, or the distortion that's caused by the turbulence out. So another way to think about this is like a circus funhouse mirror that's warped and makes, if you only look at one of them, makes you look distorted. So the goal of adaptive optics is to put in a mirror that has the exact opposite shape, or the conjugate shape, to take out the distorting effects of the Earth's atmosphere and make you look flat again. And of course, you have to do this at really rapid speeds to keep up with turbulence in the Earth's atmosphere. So typically, this is a system that's running at about 1,000 times a second. Now, before we were looking at a little inset screen, or an inset box to what was happening at the center of the galaxy. So we're only looking at that little central box to see what happens to the stars there. Now, we actually have a much bigger field of view, and we're tracking thousands and thousands of stars. But if we zoom into this scale, you can see what's going on. And at this point, it's probably helpful to think back to the beginning of this experiment, which was the early 1990s, to realize the skepticism with which people held this experiment. Because in fact, the first time we put in this experiment, proposed to use the telescope, it was turned down. It was turned down because people didn't believe our techniques, those early techniques, would work. And even if they did, we wouldn't see stars, and even if they did, we wouldn't see their motion. So I have to say, this is one of my favorite movies to watch. So on the left is what we did for the first 10 years. That was the computationally intensive but hardware simple approach. It didn't give us much. It gave us an image at a single wavelength, but it told us that there were stars there. And you can probably find my favorite star in the galaxy. Its name is S02. It probably needs a better name, but for the moment, it's a name that actually helps us identify where in the field it is. Now, the next 10 years of adaptive optics made the observations much more powerful. Now we can take measurements, images that are much deeper, so you can see far more stars. You can position these stars far more accurately. And you can take images at a number of different wavelengths, and you can take spectra for the first time. And those spectra are important for a number of reasons. One is that for the first time you get to measure the motion along your line of sight. So this movie shows you how things are moving in the plane of the sky, but you're missing the third dimension. So spectroscopy allows you to figure out how things are moving along the line of sight, and for the first time, actually allows you to explore the astrophysics of these objects. In other words, to ask, well, what kind of stars are we looking at? And I'll return to that in a moment. Now, the next animation I'm going to show you is a fourth of the real estate. I mean, this is a ridiculously small scale. If you recall back to the original animation, without any of these techniques, it's one blurry image over the scale of this image. In other words, without adaptive optics or speckle imaging, your resolution would be the size of this box. So we're going down to a fourth of the scale, and that's necessary because things are moving so fast. And I never get tired of looking at this animation either. It really describes, so this is no longer the direct data. The last images were real data. There was nothing enhanced about them. It was just the data that we get shown. Now this is an animation that shows how the brightest stars that we're measuring, not all of them, are moving over the last 25 years. So this is definitely an experiment that requires a tremendous amount of patience. In this animation, when a star is detected in an image, it's trailed by a dashed line. So you'll see that stars appear, and they're not appearing because they're getting brighter, but rather that your sensitivity, your adaptive optics has allowed us to see stars that the speckle imaging experiment didn't allow us to measure. And then when it's trailed with a solid line, we finally have the instrumentation and methodology that's allowing us to measure the spectroscopy of that particular star. So you can see that there's a time evolution in our ability to get spectra as well. Okay, so this is just getting better with time. The other thing that I'd like to take a pause to just acknowledge is that when these experiments, both those done by my group and those done by the Max Planck group, no one envisioned orbits. We were just thinking about velocities. So remember that even the idea of measuring speeds, how fast individual stars are moving on the plane of the sky, was already a challenging enough concept back in the early 90s. So the idea there was just that stars closer to the center would be moving faster on average. So you're just setting out to measure little arcs, so little line segments. So that was the first phase of the experiment, and yet people in the late 90s, by the time these experiments were being published, were questioning and suggesting that there could be all sorts of other things pushing these stars around, so we kept going. And the next thing you can kind of see from this animation is that things are going to deviate from a straight line. So then in about 2000, you could measure accelerations, and the minute you get accelerations, you understand how exciting this project is going to be, because you can foresee at that point that the orbital periods are going to be shorter than a human lifetime. And here, again, just consider that it takes the solar system 200 million years to get around the center of the galaxy, and here we're talking about things that are happening on a decade timescale. So my favorite star there is going around every 16 years. And what is that star? I mean, now we have the most direct. So the early velocity ideas was an indirect sort of statistical approach, so sort of phase 1, accelerations were phase 2, and then the orbits were really the important phase 3. With phase 3, you see an orbit that's going around every 16 years. And what does that tell us? Well, before we started this experiment, we knew that there was 4 million times the mass of the sun inside a region that's depicted here with a circle. And at this point, you're well outside the Schwarzschild radius. But what this experiment has done is to show that, in fact, there's 4 million times the mass of the sun inside a volume that's 10 million times smaller. And that volume corresponds to the scale of the solar system. So there are a couple of things to point out here. If we think about our own solar system, there's one sun worth of material there, effectively. Now we have the same region that you have 4 million times the mass of the sun crammed into that region. And this has actually increased the evidence for a supermassive black hole by a factor of 10 million. I mean, think about anything that you could move forward or increase that you'd like more of. In this case, this has been a dramatic increase, which has really moved us from the possibility of a supermassive black hole to a certainty that there's a supermassive black hole at the center of our galaxy. And not only at the center of our galaxy, but really of any other galaxy in the universe. All right, so this is really what is being recognized with this prize. But there's so much more that's happened with this work which has really given us an ability to see the center of the galaxy in a way that really hasn't been possible before. So I want to just very briefly touch upon two things. One is our ability to understand the role that supermassive black holes play in the formation and evolution of galaxies. When the work was first being announced in these various stages, the thinking about this question was very different. It was really the chicken or the egg. Which came first, the galaxy or the black hole? So this is like the chicken or the egg problem. And in fact, we had ideas for how to get either one of these scenarios to work. But today, what we recognize as more and more candidate supermassive black holes are emerging, that that's just the wrong framework. And in fact, the mass of the black hole seems to correlate with the mass of the central part of the galaxy, and called the bulge. And the scale of these two objects are so vastly different that we recognize today that whatever formed one had to result in the formation in the other, and that over time there has to be a feedback mechanism between the two. Now, one of my favorite aspects of this project is that it has allowed us not only to address the question that we set out to address, but it has raised more questions that it has answered. And this animation just shows you, touches upon a few. We anticipate, and in fact it was an early argument against the existence of a supermassive black hole, that there should be no young stars. And there were some young stars hanging around the outside of that really big circle before, which was one of the arguments against a supermassive black hole at the center of our own galaxy. And today we recognize that there is a supermassive black hole, and the stars that we were tracking right at the center are young. Okay, so I like to call that problem the paradox of youth. So we have a lot to think about. And as you can see in this, actually what I should say is in this animation, the young stars are the aqua blue. So they're actually the most dominant part of the population that we can see is the young stars, which we predict should not be there. And in this animation, as it pulls back, you can see a plane, which is providing us with a very important hint as to how those stars arrived to be where they are. We actually think that there was an episode of star formation, which probably made our galaxy look a lot like those active galactic nuclei that I mentioned to begin with in our galaxy's history. But that was millions of years ago. The other prediction is that there should be lots of old stars. Old stars have lots of time to congregate or settle into the middle, to congregate around the most massive object in the system, and that's the black hole. And the old stars are the orange things. And in fact, there's a dearth of old stars. So that's sort of paradox number two. Where are the old stars? And then the third thing that I find the most interesting is the thing that we didn't even think to make predictions for, are these objects that are being tidally torn apart as they go through closest approach to the black hole. These are objects that we can see evolve in their characteristics as they approach the black hole and then emerge out the other side. And today, we think that these are stars that have been driven to merge, so pairs of stars that have been driven to merge by the supermassive black hole. And we think this actually might illuminate important processes that connect what's happening at the center of the galaxy with the gravitational wave detections that have been recently observed with LIGO. Now, the last but not least, I want to turn my attention to using the center of the galaxy as a test or a laboratory for understanding how gravity works in this extreme environment. So we know that supermassive black holes ultimately represent the breakdown of our understanding of how gravity works, because we don't know how to make quantum mechanics and general relativity work together. And the depiction that you often see in science museums is to flatten out 3 dimensions of space into 2, and then to use the 3rd dimension as to depict time. So as you approach a black hole, you get this mixture of space and time, which is one of the predictions of relativity. And these orbits of stars are providing us with the first direct tests of how gravity works near a supermassive black hole. And there are 2 tests that are now possible. One, you can look at how photons are affected by their climbing out of the gravitational potential well. They have to give up some energy. And in fact, as this star goes through closest approach, SO2, that was actually seen. So this effect is actually best seen at closest approach. So that was seen in 2018. And I'm going to call that phase number 4. And then the next thing is the precession of the periapse, which is how the object itself moves through space and time. And this is best seen at apoapse. I should say for both of these, you need to see the orbit go all the way around once. In other words, in order to get a seat at the table for doing these next 2 projects, you have to have the measurements for the first complete orbit, which is 16 years. So there's a lot of patience to get to this next phase, but the signatures are emerging. Now, before I conclude, I'd like to acknowledge that all of this work has been done in collaboration with a number of people, and in particular with my long-term collaborators, Eric Becklin and Mark Morris, who are shown on the left, and also included in this picture is my first graduate student, Beth Klein. So this started as a small project with with 3 collaborators. Today, it's a much larger team. Today, we're a collaboration of 30 people. And along the way, over 25 years, we've had 4 or 5 generations of students who have been trained to do all sorts of wonderful things. They've gone on to academia, to industry, to the financial world, to all sorts of amazing jobs that this kind of training opens the door to. All of this work has been done with support from a large number of organizations over the last 25 years. I in particular want to acknowledge the backbone of the support, which comes from UCLA and the National Science Foundation. And then along the way, we've been so fortunate to be supported by those who support early faculty work with the Sloan Foundation, the Packard Foundation, and the MacArthur Foundation. And then more recently, we've been supported by the Keck Foundation, the Moore Foundation, and the Heising-Simons Foundation. And last but not least, I'd like to recognize the role of the Galactic Centers Group's Star Society group, in particular the chair of our board, Arthur Levine, and his wife, Lauren Leichman, who have been just amazing supporters of this work for the last few years. So let me conclude with, if nothing else, I hope I've convinced you that we have remarkable evidence for the existence of a supermassive black hole. This evidence has increased our understanding of the presence of a black hole by a factor of 10 million, which has moved the idea of black holes from a possibility to a certainty, and the revolution in technology that has come with this has opened more questions than answers. So there's more work to be done, and thank you for your attention.